Hi. Today topic is principal sources of optimization is the part of compiler design. This optimization technique can be done locally or globally. If the transformation is applied on on the same basic block, then that kind of transformation is done locally. Otherwise, transformation is done globally. Generally, the local transformations are done first. While applying the optimization or applying the optimizing transformations, the semantics of the source code should not be changed. So here we have the different types of optimization techniques we're going to use for changing of our source code. In that we are having the compile time execution, common sub expression elimination, variable propagation, code movement, strength reduction, dead code elimination. These are the different optimizing transformations we're going to be used for changing of source program. Now we will see the individually how we're going to be transforming the source code. First one is compile time evaluation. In this compile time evaluation means shifting of computations from runtime to compilation time. There are the two methods used to obtain the compile time evaluations. One is folding, another one is constant propagation. A folding is a technique. The computation of constant is done at compile time instead of execution time. Here we have the example. Suppose length equal to 22 by 7 into d. Here the folding is applied by performing the computation of 22 by 7 at compile time instead of execution time. In the constant propagation, this is a technique. The value of variable is replaced and computation of an expression is done at the compile time. That means we're going to be using the variables which are going to be replaced at the time of compile time. Here we're having the example like pi equal to 3.14 and r equal to 5. We're going to be substituting the pi value and r value in the formula. That is area equal to pi into r star r. Here at the compile time, the value of pi is replaced by 3.14 and r value will be replaced by 5. Then computation of 3.14 into r is done during the compilation. This is the compile time evolution with the two two methods, that is folding and constant propagation. Now coming to the common sub expression evolution. The common sub expression is an expression appearing repeatedly in the program which is computed previously. That is already we have some expression which is already occurred in the program that is going to be repeated multiple times. Then if the operands of this sub expression do not get changed at all the time in the result of sub expression is used instead of recomputing it each time. That is where we are not recomputing the entire thing. Here we have the example with t1 equal to 4 into I. Here we have the T1 equal temporary 1 equal to 4 into I. Temporary 2 equal to A of T1. That is, this value is stored. 3 to, that is temporary 3 equal to 4 into J. Yeah, T4 equal to 4 into I again. Temporary 5 equal to N. Temporary 6 equal to B of T4 plus T5. Right? Here we are going to be reducing the or eliminating the repeated expression. Here we can see that T4 equal to 4 into I. It is already repeated value. It will be available at temporary 1 equal 4 into I. Both are the same. So here already this is the first occurrence. This is the second occurrence. So we are going to be eliminating the T4. So finally we are going to get the like this. T4 is eliminated. T1 equal to 4 into I. T2 equal to A of T1. T3 equal to 4 into J. T5 equal to N. T6 equal to T of sorry B of T4 plus T5. Clear? Right, small change here. Right here we have to change that. We already here we removed the T4, so that instead of T4 we are going to get the T1. Why means T1 and T4 are same, so that we are going to get the T1 value here. Clear? The common sub expressions T4 is eliminated as the computation is already in T1 and the value of I is not being changed from the definition to use. This is about the common sub expression elimination. Next, we have the variable propagation. Variable propagation means use of one variable instead of another. That we're going to be using the another variable instead of one variable. For example, here we consider that x equal to pi, right? Area equal to x into r into r. The optimization using variable propagation can be done as follows. That is, area equal to pi into r into r. Here the variable x is eliminated, so that we are going to consider that pi here. That is the variable propagation. Next, we are having the code movement, right? The two here there are the two basic goals of code movement: to reduce the size of the code, that is to obtain the space complexity. Another one is to reduce the frequency of execution of code, that is to obtain the time complexity. Here we're going to talking about the both space complexity and the time complexity. So here we have the example to better understanding. For loop I equal to 0, I less than equal to 10, I plus plus, open braces, x equal to y into 5, and so on, k equal to y into I plus 50. This is the code we return. This can be optimized as next the code movement. The code movement can be having the two basic goals. One is to reduce the code and frequently execution of the code. The reducing of the code will be discussed about the space complexity. Execution of the code will be discussed about the time complexity. But here we have the example for I equal to 0, I less than or equal to 10, and I plus plus braces, y equal to x equal to y into 5, and so on. K equal to, within the parenthesis, y into 5 plus 50. Close the braces. Now we are going to be reducing the code by writing the z. That means we are going to be replacing this expression y into x, so y into 5, you're going to be replacing that y into 5. This one is going to be replaced with z. Here I am right. Here I am writing that z. Here also it is going to be replaced with z. And here we are going to be defining that z equal to x into y before the for loop. Let us see how I wrote the code. Z equal to y into 5 for I equal to 0, L is equal to 10, I plus plus, z equal to 5 instead, sorry, x equal to z instead of y into 5. Already we defined that z equal to y into 5, so that x equal to z, k equal to z plus 50. This way we are going to be changing the code. The code for y into 5 will be generated only once, and simply the result of the computation is used whenever necessary. Next one is loop invariant computation. Loop invariant computation is optimization can be obtained by moving some amount of code outside the loop and placing it just entering in the loop. This method is also called as code motion. This method is also called it as code motion. Here we have the example for understanding. While I less than equal max minus 1, the condition is, I write in the condition while condition I less than equal to max minus 1. Open the braces, curly braces, sum equal to sum plus a of I. The above code, this code can be obtained by removing the computation of max minus 1 outside the loop. The optimization code can be written as, I can write that n equal to max minus 1. I'm going to be removing the max outside and writing that n equal to max minus 1. Now simply I can write that while I less than or equal to n. See that how I am going to write n equal to max minus 1 while I less than or equal to n, and remaining all of the same. This gives the loop invariant computation. Next we have the strength reduction. The strength of certain operations is higher than others. For instance, the strength of star is greater than or higher than plus. The strength reduction technique, the higher strength operators can be replaced by low strength operations. So we're going to be replacing with alternate. Instead of star, we're going to be replacing with plus. Like that, whatever we have the equivalent operations, it can be replaced. For example, here I wrote the for loop I equal to 1, I less than equal to 50, and I increment. The count equal to I plus 7. Here we got the count values as 7 comma 14 comma 21 and so on up to less than 50. The condition is given up to less than or equal to 50. So it starts from 1, that is 1 into 7, 2 into 7, 3 into 7, 4 into 7, like that up to less than 50 it is going to be displaying. For that I changed the code and wrote that as temp equal to 7. Instead of star, I am going to be using the plus. Instead of that, I am going to be using that plus, right? So that here I wrote the temp equal to 7 for loop as it is, count equal to temp, that is count equal to 7. then the temp equal to temp plus 7. So we will get that first initially we are going to get the 7. After that 7 plus 7, that is 14. 14 will be stored in the temp. After that again plus 7, that is third time. Like that it is going to be increasing the value. Clear? There is no change in the program, but only the syntax has been changed. Thus we get the value of count as 7, 14, 21, and so on up to less than 50. The induction variable, or the induction variable is integer scalar, identifies the user in that form of v equal to v plus or minus constant. Here v is an induction variable. The strength reduction is not applied to the floating point expressions because such a user may yield different results. So we are not going to be applying this for the floating values. Next we have the dead code elimination. A variable is said to be live in a program if the value contains into it is used in the subsequently. That is, we're going to be generating some variable. It has been used under the program in subsequently. On other hand, the variable is said to be dead at the point in a program it if the value contained in it is never been used. If you are not using that variable means we can say that it is a dead value. The code containing such a variable is supposed to be dead code, and an automation can be performed by eliminating such dead code. We're going to be eliminating such dead code. For example, we have that I equal to j and k and x equal to I plus 10. The automation can be performed by eliminating the assignment statement I equal to j. This right. This is the I equal to j assignment operator assignment statement is called the dead assignment because we are not going to be using the I equal to j anywhere. Why means j is not available value in the given expression. So that this is called the dead assignment. In the same way, we can say that another example I equal to 0. Suppose I am saying that I equal to 0, and I'm going to write in that if I equal to 1 open braces, and I'm writing that if I equal to 1 open braces a equal to x plus 5 and close braces. Here if statement is a dead as this condition will be never get satisfied. Hence, if the statement can be eliminated and optimization can be done. Right here we are going to using that if statement. If statement will not be used for never, so that we can say that the code is dead at the time of the condition. This is about the dead code elimination. But this covers the principles sources of optimization. I hope that you understand this topic.